This diagram shows the Earth orbiting around the Sun, but the truth is that all the equations that we're going to look at can be applied to any object orbiting around any other object. There's going to be a gravitational force of attraction F here, which we can determine using Newton's law of gravitation, F equals gmm over r squared. And as the Earth moves around, as it orbits around, the force is always going to be pointing toward the center, because that's providing a centripetal force. So we can also use the equations, circular motion equations. For example, the centripetal force equation like this, mv squared over r. So where v is the time it takes to do, is the speed around of the Earth around the Sun. So that can be determined using the circumference divided by the time period, 2 pi r divided by capital T, which is a time period. We could also use F equals m omega squared r, where omega is 2 pi over T. Now, the velocity of the Earth as it goes around is always going to be at 90 degrees to the force. So you can't quite see from the diagram, but it should always be moving at 90 degrees to the force. So this is important because that means no work is going to be done by the gravitational force. Okay, that's because the definition of work done is should be force times distance moved parallel to the force. But it never moves parallel to force, it was always moving perpendicular to force. So this is why the kinetic energy doesn't change, and neither does the gravitational potential energy at that particular radius of orbit. Kepler's third law states that for an object in circular orbit around a planet or a star, the time period and the radius of orbit are related by t squared is proportional to r cubed. Derive this relationship. Okay, I'm going to use the Earth going around the Sun as an example here. So there's going to be a centripetal force to keep it going in circular orbit. So I'm actually not going to use mv squared. If I'm going to use m omega squared r, because this will be easier to bring in the time period in a second. Okay, so the centripetal force is provided by the gravitational attraction. So I can use Newton's law of gravitation to get rid of the F here. So I get this equation here where I've replaced F with the Newton's law of gravitation. I'm going to get rid of omega, okay, because I need to bring in time period. And omega and time period are related through the equation omega equals 2 pi over t. So if I put that in there instead of omega, and I have to square it because you can see the omega is being squared. So let me expand this bracket here. So the 2 pi over t squared becomes 4 pi squared over t squared. As then you can see I'm going to start simplifying this. The m's, there's lowercase m, which is the mass of the Earth in this example, but basically the mass of the object that's doing the orbiting. I'm going to cancel that out. Okay, then I'm going to move around some stuff. So I'm going to bring the r squared from the bottom on the left hand side to the right hand side, where it's going to become r cubed. Okay, then I'm going to bring the t squared to the left hand side, so it's going to come to the top, and I'm going to bring the gm down, like so. So now we've got the equation that we've been looking for. T squared is proportional to r cubed, and the constant of proportionality in this case is 4 pi squared over gm. Okay, this gives us Kepler's third law, which is very useful studying when a number of objects are orbiting around a central object. For example, planets around a star, or satellites around a planet in the middle, or even moons around a planet in the middle as well. It's useful because this number at the front here, 4 pi squared over gm, is going to be a constant for all of those objects. So the capital M here is the mass in the middle. So in the case of our solar system, it's going to be the mass of the sun. So this equation tells us that the further an object is from the center, the longer the time period. So you can see here Neptune is much further than the Earth from the center of our galaxy or solar system, so it takes a longer time period to do an orbit. Okay, in this example, the radius of Jupiter's orbit around the Sun is 5.2 times greater than Earth's orbit around the Sun. So calculate time period of Jupiter's orbit in Earth days. Okay, so we can use Kepler's law here to study the relation between radius of orbit and time period. And we can get rid of all the constants in the middle because they're all the same for all those objects, so we can use it as a proportionality question. I'm going to make time period the subject because I'm interested in what's going to happen to time period. I know that the radius of Jupiter's orbit is 5.2 times bigger, but that's going to get cubed first, and then it's going to be under a square root. So if I put this into calculator, I get the time period of Jupiter's orbit is 11.8 times longer. Now it takes the Earth 365 days to go around. So that's the time period of Earth's orbit around the Sun. So if I times that by 11.8 times bigger, it takes a Jupiter 4,328 days, which is obviously much longer. In this final example, calculate the height of the geostationary satellites above the surface of the Earth. So geostationary satellites have a fixed position in the sky, so it means that they orbit around at the same time period as the rotation of the Earth. So they have a time period of 24 hours. I'm going to turn this into seconds by times it by 60 minutes and 60 seconds. So that gives me a total of these many seconds. Then I'm going to use Kepler's law, okay, to work out the height. Actually, I'm going to work out the distance from the center, and then I'm going to work out the height. So I'm going to rearrange this to make R the subject, like this carefully, and then I'm going to put the numbers in. So I'm going to take this cube root of t squared, and the time period is this, and I'm going to square it, times it by a gravitational constant, capital G, times by the mass in the middle, which is the Earth here. So that's from your data sheets there, divided by 4 pi squared. Okay, and then that gives me a radius of orbit of 4.44 times 10 to 7 meters. Now from that, I'm going to have to subtract the radius of the Earth because the question is asking for the height above the surface. The radius of the Earth is going to be either provided or is going to be in your data sheets, and that gives you the height of orbit around above the Earth's surface.